fundamental theorem of calculus. So after this topic, we will move to the multivariable functions. So functions of two variables and more variables. So there are basically two types of two versions of fundamental theorem. First is of first type and second type. So let us first state the first fundamental theorem. So this theorem says that if we have an integrable function on closed interval AB, then for all a less than or equal to x less than or equal to b, we can consider the integral new related function, that is capital F of x. So small f is given function. We are considering a related function which is capital Fx, and that we are defining from x to a, integral x to a of the original function. So this is basically the if we have the interval a to b and x is any point in between, it may be any point in between a and b, then this integral, we know that it is area under the curve fx between a and x, right? So that is this function. This area function is capital Fx basically. So we want to see when this function is continuous and when this function is differentiable. So the first fundamental theorem says that whenever small f function is integrable function over the closed interval AB, then this area function capital F, which is area between a to x of the function, is always continuous function. So continuity of capital F is implies from the integrability of the given function small f. But what about the differentiability of capital F function? So for that we need an extra condition. So that is that moreover, if our given function small f function is continuous, on the interval. So if this condition is satisfied, that given function is continuous on the entire interval, then capital F function is differentiable. So what this gives is that this function is differentiable and we get its derivative at the point x0 is f of x0. So f is continuous basically at the point x0 in this interval. So wherever the function small f is continuous, this capital F function is differentiable, and at that point we have this relation. So this is the complete statement of the theorem, which is known as the first fundamental theorem of calculus. So this capital F function is known as the antiderivative of the small f function. So note that the function capital F here is called the antiderivative of the given function f. So small f function is given when we integrate it from a to x, we get the antiderivative of the function. So this is first fundamental theorem. Now let us see what is the statement of the second fundamental theorem. So later on we will see some example where we will apply first fundamental theorem. Second fundamental theorem we already applying on many times when we use the integration. So second fundamental theorem says that whenever we have a function which is integrable, so let f be an integrable function on the interval close interval a to b, and if there exists a differentiable function capital F on close interval ab such that derivative of this capital function is small f, right? So this is basically the antiderivative of the given function f, and in this case what we get is whenever we integrate a to b fx dx, it is essentially so what we use every time is that whenever we have a function which is a which is derivative of some function, then this is basically f dash x dx, and then we evaluate the function at the point from x equal to a to x equal to t. So this is what whenever we integrate a function we use this theorem. So this is nothing but fb minus fa. So this is second fundamental theorem when the function should be integrable and whenever it is derivative of some function. So second theorem we usually apply whenever we integrate and substitute the limit of some function. But let us see when we can apply the first fundamental theorem of calculus. So let p be a fixed number, fixed positive number, and we have a function which is continuous on R, which satisfies it satisfies the relation x plus p equal to fx for all real number x. So do we remember any function fx which satisfies this property?
Sin x हो जाएगा, मतलब periodic function है basically.
Exactly. So right. So this such a function is called the periodic function, and this number p, which is greater than 0, is known as the period of the function. So the number p greater than 0 is called the period of the function. So as you said, the example is fx equal to sin x or cos x, and here p is 2 pi. So what we want to prove here is that we want to show that the integral a to a plus p of ft dt has the same value for every real number a greater than 0. So here basically a is fixed, but we can check we can change a. So we can take a equal to 0. Then since for the sin x function p is 2 times p, so integration 0 to 2 pi sin x dx, that is what we will get, and that area will be same for every a. If we change a also, the the integration of the sin x function between any interval of size 2 times pi will be the same. So that is what we want to show here. So whatever function we are given, f, which is continuous function on R and which is periodic, then its integral is always same if the length of the interval is the period basically. So now let us so how we can apply this theorem here. So let us see what is the first fundamental theorem statement. So in the first fundamental theorem, basically we integrate the function from a to x, right? So a is a fixed number from which we are finding the integral. So what we usually choose is we take a equal to 0 there, right? So let us see what we will do here. So note that a is greater than 0 and p is greater than 0. So using the first fundamental theorem, of calculus, basically we want to find integration a to a plus p ft dt, but the first fundamental theorem is for the integration from some fixed number a which may be different from this a and to a particular number. So to use that theorem, what we need to do is we have to integrate the function f2 dt into we should divide in two parts. First part is a to a plus p, and we can subtract integral 0 to a ft dt, right? So we can divide this area into two parts because the function is defined over the whole real line. So f is defined over the whole real line. F is function from R to R. So we can integrate it from 0 to a plus p, and it is continuous also. So now what we will do is we will differentiate both the sides. So if we differentiate both the sides, we will differentiate by the variable a, because a is changing here. So on the side, if we differentiate, we will get derivative of this function. So now we can separate these terms. So this is derivative of 0 to a plus p ft dt minus derivative of 0 to a ft dt. So here basically we use p is greater than 0. So a plus p is bigger than a. Right? And then now we can apply the fundamental theorem of calculus. So fundamental theorem of calculus says that whenever we differentiate the function, this particular function, then what we get is we get the value of the function at that particular point. So if we differentiate this function, what we'll get is f of a plus p minus f of a, right? So that is the thing we'll get, and then finally what we get, f is a periodic function. So f is periodic function means what property is given is f of x plus p is same as f of x. So that we can use here. So finally we'll get f of a plus p minus fa is equal to 0. Right. So this gives us that whenever we differentiate this particular function,
सर जीरो कैसे आया समझ नहीं आया इक्वल कैसे आपने प्रूव करा उसे
so f of a is any point. So what is given is f of x plus p is fx for every x equal to x real number x. So now in particular we are taking x equal to a because a is a real number. So what we get is f of a plus p is equal to f of a. So since f of a plus p is equal to f of a plus p minus fa is 0.
सर तो हमें जो क्वेश्चन में फंक्शन दिया हुआ है वो हमें पीरियोडिक दिया हुआ है
Yes, that is given. So that is given in the statement of the example.
Okay, sir.
So what is given is that f is a continuous periodic function, and what we want to show is that this integral is always a fixed number. So to show that integral is always a fixed number, what we will show is that derivative of
Yes, sir.
this
Derivative is zero, so
function
मतलब जो
zero.
function होगा वो constant होगा.
Right. So derivative we have shown that we have got is 0, and this is 0 for every value of a. So it is entirely 0 function. Derivative is entirely 0 function. So therefore the integral a to a plus b is a constant function. So this is a first example. Let us see related another example. So if we have a continuous function, on the closed interval 0 to pi by 2. and this function has the area okay, so this PDF is over. So let me go to the next video. So and the second condition given is that the area from 0 to pi by 2 of this function is 0. So then we want to prove that there exists a positive number in the open interval such that f of c is equal to 2 cosine 2c. So let us see the question again. So question is that just a minute. So question is that f is a continuous function on closed interval 0 to pi by 2 and for which the area in the interval is 0 of the function. Then we want to prove that there exists a point c in the open interval such that fc equal to 2 cosine 2c. So by the statement it seems that we are basically using kind of Min value theorem, right? Because c is in the open interval. So here what we will do is we will combine the Min value theorem with the first fundamental theorem of calculus. So define a function such that the function fx is the area function 0 to x 50 dt. So now why we are integrating from 0 to x? Because the left end point of the interval is 0, right? So therefore we are integrating from 0 to x and minus sine 2t. So we are taking this particular function because you can see that when we'll differentiate this function, essentially we'll get derivative of this will be f of x by the first fundamental theorem, and derivative of this function will be 2 times cos 2x, right? So this is the reason why we are taking capital Fx to be this function. So note that this function, note that f is continuous, therefore what we have is that derivative of f dash x is fx for every x in the interval. Right. So therefore what will be the derivative of capital yeah, so this is a mistake actually. So derivative of the integral basically, right? So this is coming from the first fundamental theorem, because first fundamental theorem, right? So now if we use this for this particular function, so if we differentiate this particular function capital X, then what we get f dash x to be derivative of 0 to x ft dt minus derivative of sine 2x, right? So now if we use the first fundamental theorem, what we get is we get fx minus 2 cosine 2x. Right. So that is what we get. And since the given function capital Fx is also continuous and differentiable on so let us note that capital Fx is continuous on interval 0 to pi by 2 and differentiable on the open interval. We can apply the Min Value Theorem.
Sir,
Yes. Yes, any doubt?
सर ये जो f of 0 है, small f of 0, इसको 0 कैसे कहा?
Yes, f of 0 is f of 0 we did not verify. So yes, you're right. So that we need to check, right? So so you are basically saying that the one condition of the Min Value Theorem is we have to check that at the end point the function should be same. So you're right. So let us check that. So differentiable on this and yeah. So two things we need to check. We need to check f of 0 as well as f of pi by 2. So f of 0 is 0. Is it clear? Because our function is this one. So we know that sine, if we substitute capital F of 0, then sine 2 times 0 is 0 because sine of 0 is 0.
Right, sir, जब हमने small f of t को differentiate किया था, तब हमने उसे fx plus 2 cos 2x लिखा था, तो उसमें मतलब f of 0 भी आएगा ना, fx minus f of 0 plus 2 cos 2x.
No, this is just simple derivative of the sine 2x function. So this
small
capital
का integration में वो 0 जो small x का integration
integral is up to this only. This is a separate function of x.
हाँ सर, बट जब इस जो ये इंटीग्रल है सर, उसको जब हमने डिफरेंशिएट किया नीचे वाले पेज में सबसे टॉप पे सर, हाँ सर, कंटिन्यूअस देयरफॉर के बाद तो सर वहां पे माइनस f0 भी तो आनी चाहिए। f0 की टर्म हम 0 ऐसे कर रहे हैं,
तो वो 0 into f0 आएगी ना।
हाँ, वो तो न्यूटन लिबनिट्ज लगा रहा है, पर जैसे वो तो सीधा जैसे करना है, जैसे
डेरिवेटिव ऑफ x into f of x माइनस डेरिवेटिव ऑफ 0 into f of 0,
तो वो 0 ही आएगा।
हाँ वो 0 ही हो जाएगी वो वाली टर्म।
ठीक है।
So this is actually coming from the first fundamental theorem. So I think that 0 term won't come here. See, if we integrate the derivative of, then we get that term and we need to substitute that. But here it is different. Here basically we are differentiating the function which is in terms of integral. So that is not the usual case when we are applying the integral on the derivative of a function. Here we are applying the derivative on the integral of the function. And if you want to see the definition, the proof of the first fundamental theorem, it is given in the footnotes. So if you have doubt that constant term is coming or not, we can check later on. But as far I remember, that term won't come. Okay. So let us first check that this capital F function, whether it satisfies all the properties of the the mean value theorem. So to check that, we have to check value of capital F function at the endpoint. So f of 0 is 0 because the area of the function from point 0 to 0 is always 0, and sine 2 times 0 is 0. So capital F0 is 0, and capital F at pi by 2 is basically the area from 0 to pi by 2 ft dt minus 2 times sine 2 pi by 2. Alright, our function is sine 2x, so 2 will not come there. And then sine pi is 0, and this area is 0, that is given in the statement. What is given in the statement? Area is 0 of the function from 0 to pi by 2, right? So that we can use here. So basically it is 0 minus 0, and finally it is 0. So now all the condition of mean value theorem is satisfied, so therefore we can apply mean value theorem on capital F. So if we apply mean value theorem on capital F function over the interval 0 to pi by 2, what we get is that f pi by 2 minus f0 is equal to f dash c into b minus a, right? And where c is the point between 0 and pi by 2.
सर ये आपने रोल्स मीन वैल्यू थ्योरम लगाई है ना, वो रोल्स मीन वैल्यू थ्योरम ही f of a equals to f of b.
Okay, right. So here b, f of b and f of a is same, so therefore basically this value is 0. So you are right. So we can directly apply the Rolle's mean value theorem. So we can directly write that derivative is 0. Right. And then derivative we already have checked. So what is the derivative? Derivative of capital F function is this, but now we need to evaluate it at the point x equal to c. So therefore we get f of c equal to 2 cosine 2 times c. Okay, so let us just let me just show all the solution once again. So we started with the function f, which is continuous on the closed interval 0 to pi by 2, and it satisfies the integral of the function is 0, right? So we want to show that there exists a point c in the open interval 0 to pi by 2 such that this condition is satisfied. So since we need to find the c point between 0 and pi by 2, we have guessed that we need to apply the mean value theorem, and since we need this particular equation, and this is derivative of the integration 0 to x ft dt, we have taken integration of this function basically as the difference function. So we consider this capital F function, we could have said it capital Gx, because basically it is a function of x, but we are using the same symbol capital Fx. So do not confuse with the function we considered in the first fundamental theorem. This is different function. So this is basically the function of the first fundamental theorem. It's different with another function sine 2x, and then we check that by first fundamental theorem the derivative of this function is capital Fx, and derivative of sine 2x is 2 cos 2x, right? So then we apply the mean value theorem, because capital F of 0 is capital F of pi by 2, and the function is differentiable on closed interval. It is uh, it is uh, it is differentiable on open interval, continuous on closed interval. So by applying the mean value theorem, Rolle's mean value theorem, basically we get there exists a point C in the interval 0 to pi by 2 such that f of C is equal to 2 cosine 2 times C. So so this is basically regarding the fundamental theorem of calculus. We discuss one or two examples here. So now onwards we will discuss the multivariable functions. So they are called functions of several variables. So functions of several variables means so far we have discussed functions which are from real line to real line, real numbers to real numbers. But now we will discuss functions f where the domain is subset of xy plane and it is taking values in R. So for example, the function I am defining is f of xy equal to xy divided by square root x square plus y square and 0. So whenever xy is not origin, and if xy is equal to 0 comma 0, then I'm defining value of the function to be 0. So here you can see that function is defined on two variables. So in particular, what will be the value of 1 comma 0? So value of 1 comma 0. So this 1 comma 0 is not equal to 0 0. So it comes here. So therefore we need to apply this function here. So that is nothing but x is 1, y is 0 divided by x is 1, y is 0, right? So essentially we'll get numerator is 0, denominator is 1. So finally the value of the function is 0 at this particular point. Right, what is f of 0 0? So 0 comma 0, the value of the function is already given to be 0. So we'll apply the direct definition of function.
सर एक बार प्लीज थोड़ा सा स्क्रॉल अप करेंगे जहाँ इशू होगा.
So basically we are defining the function which are defined on the xy plane. So function is, we are evaluating at the value of the xy plane, but the output of the function, the value of the function at that point is a real number. So this is a real number, this is also a real number, but this is in xy plane, so it belongs to R2. It is a pair of two real numbers. Right, what will be f of 1 comma minus 2? It again comes in this definition, so that will be 1 into minus 2 divided by square root 1 square plus minus 2 square. So that is minus 2 divided by square root of 1 plus 4. So finally it is minus 2 by root 5. So let us take one simple example, definition and example, then I will stop today. So a function f defined on the whole real line to real line is called homogeneous function of degree n if it satisfies certain condition. So condition is that f, when we evaluate it at tx ty, then it will be t power n xy, f of xy, for all real numbers x and y. So we need to check this particular condition. So what is the condition? Condition is we apply function on tx comma ty, and on the right side we will get the original function f of xy, and it will be multiplied to some power of t. So every function need not satisfy this condition, but whenever we can write this function f of tx comma ty is equal to t power n f of xy. If some function satisfies this property for some n, then such a function are known as the homogeneous function. So let us see one example that if we take f of xy equal to xy divided by x square plus y square, if xy is not equal to 0, 0, and the value is 0 if xy is 0, 0. If we have such a function which is defined from R to R, let us see if we can verify it is homogeneous or not. It may be homogeneous, it may not be homogeneous. So that depends on whether some power of t we can take common or not. So for that we need to find this value. So if substitute tx ty here, if this is 0, if f of xy is 0, then f of tx ty is also 0. So in this case, it's trivially satisfying this property, right? So we need to check only this case. So for that, f of tx ty will be tx into ty divided by tx square into ty square, right? So that is what, depending on what function we are given. So now if we take power of t, which is common in numerator and denominator, what we will get? We will get t square xy in the, so plus sign I forgot, right? So we need to write plus here because the function in the denominator is x square plus y square. So what we get is in the denominator is t square x square plus y square. Right? T square I have taken common. So now we can see this is our original function, that is xy divided by x square plus y square, right? So that is exactly the given function. So that we can write down here. So what we'll get essentially is t power 2 minus 2 f of xy. So basically we are getting t power 0 f of xy. So this is homogeneous function of degree 0, right? So whatever power comes, this power of t is basically the degree n. So here the power coming is t power 0, so basically it is 1. t is a real number, so this is nothing but f of xy. Right, so you can also define some functions similarly and check